so well, it's my pleasure to introduce Andy Manion today, and he's going to tell us about higher representations and cornered Heegaard Floer homology. So take it away.
Thank you very much for the invitation. Thank you all for coming. I am going to talk about this, higher representations, cornered Heegaard Floer homology. This is joint work with Raphael Rouquier, and largely based on a preprint that we posted last September, although some things that I'll be talking about today are sort of perspectives that we didn't write up in that paper, but there's sort of a lot of angles you could take on this. So I'm going to try to take a more symplectic angle than maybe what's written in the paper. So hopefully that's successful. We will see how that goes. Definitely stop for questions at any time. But we're going to start by looking at sort of the general concept of Heegaard Floer invariance of surfaces, and those are related to partially wrapped Fukaya categories of symmetric powers of those surfaces. Then we'll look at the so-called bordered strands algebras, which are known to give a combinatorial description of these things in some cases. And then the main point of the talk is going to be about what cornered Heegaard Floer homology tries to do, which is one thing it tries to do is glue together the strands algebras or the Fukaya categories for larger surfaces from smaller pieces. And that is something that I want to argue is related to higher representation theory and a certain tensor product operation for higher representations that's new. So that's what I want to get to by the end. But let's start from Heegaard Floer homology. So Heegaard Floer homology, I like to call it a TQFT. Some people complain loudly if you use those 4 letters for Heegaard Floer homology. It is a 4-letter word, but I don't think it's such an offensive one. I don't mean that it satisfies all sorts of axioms which it's known to not satisfy. Okay, I just want to make that clear. I'm not claiming it satisfies things that it's known not to. I'm just saying that physically speaking, at least, it comes from this world of quantum field theories somehow that are metric independent in some sense on some manifolds. And in this case, was first studied with gauge theory and Seiberg-Witten theory. What Heegaard Floer homology does is give a different approach a priori to computing something that's now known through a lot of work to be isomorphic, at least for 3 manifolds, to Seiberg-Witten Floer homology. And the perspective of Heegaard Floer kind of is based on what you assign to a surface. It starts by saying, well, for a surface, I want to take a Fukaya category of the symmetric product. That's like the basic idea. And then you apply that to Heegaard splittings. So a priori, that idea in the basic definitions of Heegaard Floer is just being defined, just being applied to Heegaard splittings. But more generally, you can say Heegaard Floer homology through the theory of bordered Heegaard Floer homology, first studied by Lipschitz, Oshwald, and Thurston. This sort of tries to go in more detail, look at the 2-dimensional and 3D relative structure of Heegaard Floer homology, and say in a slightly more general setting that Heegaard Floer homology assigns some sort of Fukaya categories of symmetric products to a surface, and then to 3D cobordisms that maybe aren't part of a handle body or a Heegaard decomposition. You can still talk about maybe functors between Fukaya categories induced by these, or bimodules over corresponding algebras. Okay, so the invariance of surfaces, I claim, are an important part of Heegaard Floer homology if you want to compute the 3D and 4D structure, but also just for understanding what's going on, there's this extended TQFT philosophy, and the fact that Heegaard Floer is based in some sense on invariance for surfaces already, in my mind, places it somewhat close to this extended TQFT framework. Then you can ask about going down as well. So extended TQFT would have invariance for some type of manifolds of some type of lower dimensional things down to dimension 0 maybe, or not. And I'm not saying necessarily that I know the axioms that such a theory should satisfy, just that I think that it's fruitful to try to assign things to these lower dimensional manifolds in certain cases and try to prove theorems. So it can help understanding, for instance, computing the higher dimensional things by cutting and gluing, okay? But I want to focus on something a little bit more precise, which is the type of surface that gets assigned an invariance in Heegaard Floer homology. And this is a little bit controversial because if you take the LOT viewpoint, you would say, well, it's a closed surface with a base point chosen. And I hope that since I'm speaking to a more symplectic audience, I won't have to try to sell too much, that instead one wants a surface with boundary and certain stop data on the boundary so that one can take a partially wrapped Fukaya category, and that type of surface with boundary is more directly what's getting assigned an invariant. So that's the perspective I want to take, at least in this talk. You can take other ones, but I want to consider these things that Rumanzarov calls sutured surfaces, and in analogy to sutured three manifolds. Okay, so a sutured surface is a compact oriented surface F, and then it's got stops in its boundary. So it can be just finite collection of, maybe full circles in the boundary are stopped, and then maybe, you have other boundary circles of F where you have some intervals chosen, finitely many intervals in that circle, and you say that's stopped, and S minus is Zarev's language for the part that's stopped. Okay, and then you let S plus be the sort of unstopped part of the boundary, really the closure of it, and they intersect in this zero manifold called lambda, that's in some sense, some vague sense, analogous to a set of sutures in a sutured three manifold. So this theory interacts well with sutured Floer homology. When you define Heegaard Floer invariance for this sort of stuff, then that works well with sutured Floer. So this is what Zarev does. This is an example. And this maybe or maybe not would actually fit Zarev's restrictions on these things, but I'm going to allow, for instance, a whole circle that's not stopped. So I'm going to draw the stopped bit. This is all following the notation of Rumanzarev's thesis, but the stopped part I draw in black, and then the unstopped part I draw in orange. And so these circles, so the only stop is this one interval stop on the boundary. And this will be a kind of running example. This is an example of a sutured surface. Okay, so such a thing should get assigned an invariant by Heegaard Floer homology, some sort of Fukaya category. And it's actually, if you want it to really be an invariant of the surface, you probably want to take a derived Fukaya category, this d pi, this idempotent completion of, homotopy category of twisted complexes. And then, well, what are we taking d pi of? It's a sum of partially wrapped Fukaya categories for all possible symmetric products. But for high enough k, these are going to be equivalent to 0. So you really only have to take like finitely many k, but a priori you could take sim k for all k. And this is a triangulated category, which I guess in my mind already looks like in the future will probably, there's, especially if I think that TQFT are good letters to use, it may also be the case that one does infinity categorical versions of this at some point, but I don't want to talk about that. But here I'm just indicating, so I have this in F, I have this stop subset S minus, that gives me a stop subset in the boundary of this sim k of F. And that's just, well, sim k is just all unordered k tuples of points. And then if any one of those points is in the S minus, the black part of the boundary, then my k tuple is in the stop subset of sim k. Okay, so that's my stops in sim k, and I can take a partially wrapped Fukaya category, which I'm not an expert on details, so I hope I don't get asked too many technical questions about such things. And then one takes a derived category, and then one, with the derived thing, you can show that it's an invariant up to equivalence of derived categories. Disjoint union over k with no interaction between the different factors. That's right, which seems a little bit strange, right? Shouldn't it be some more unitary mathematical object? What I'm going to be arguing by the end of this talk is that, in fact, this category should not be viewed as the entire Heegaard Floer surface invariant. Rather, it should be this category equipped with a certain higher action of a monoidal category, and that action has things that change the k. Okay, so that sort of makes it a more unitary looking single thing that's assigned to the surface in some sense. But more on that soon. I just want to mention that I don't know, right? I hope that there's I sort of have this optimism that these sutured surfaces, the picture that I draw kind of looks like it has, dimension 0, 1, and 2 features going on here. So perhaps there's something one can assign to a point. That's something that I think would be really great. Well, hopefully we'll have more to say about that in the future, but not in this talk so much.
Sorry. Point means k equals 0.
Point would mean like, this is what gets assigned to a surface, but what you could maybe say that something associated to that monoidal category acting on these things would be what's assigned to an interval.
I see.
And then if you know it's assigned to an interval, that's closely related to what's assigned to a point, if
Okay.
something is assigned to a point in the end. And so that sort of speculation is what I'm currently entertaining, although it is not something I can really say anything precise. It's something I want to be true. But, I want to be eventually true in some form. I'm looking for something that's true. But that's sort of the way I'm thinking about this, is that these sutured surfaces are very natural things to be trying to assign, and maybe in some extended TQFT sense, they're going to be a natural thing that gets assigned an invariant that no one can complain about, that this is very standard type of thing. If you do it in the right way, you get assigned an invariant. Okay, so what type of invariant? This Fukaya category, but that's a priori hard to compute with. Well, what's known about this is a very nice description in terms of an explicit algebra that's defined by some basis of pictures and then multiplication on pictures and relations on, well, it's a basis, so it's not really generated in relations so much as, you know, a set of pictures that gives a basis and then a multiplication rule and a differential. Okay, and so some algebra A, the derived category of DG modules over A, or of twisted complexes, that's equivalent to this Heegaard Floer surface invariant of the sutured surface. Okay, and what this is the endomorphism algebra of a generating set of Lagrangians, which is why you would have a derived equivalence like this. And the point is that if I have a sutured surface, then there's various ways to represent that more combinatorially, to pick something that's kind of like a triangulation or a parametrization of it, but it's a slightly different type of surface representation called the arc diagram. Sometimes I call these chord diagrams. I'll call them arc diagrams in this talk, following Zarev. But anytime I pick one of these arc diagrams, and I'll explain how this works with pictures in the next few slides, but just as a summary, anytime I pick one of these arc diagrams, then I get a generating set of Lagrangians. It's not obvious that they generate. That was kind of the hardest part of all of this, as I understand. But you get some Lagrangians, and then you have some endomorphism algebra. And then the other part of this is that this endomorphism algebra of the Lagrangians you get, given an arc diagram Z, then admits this alternate picture-based description. And that's a kind of nice argument involving combinatorics of a certain Heegaard diagram. So that's more or less how this works. I want to say, so this is due to Aru, of course. It's relatively probably familiar to this audience. But so this is, for instance, in his ICM address in 2010. And but I want to say a little bit more about what's going on here and what are the players in this story, because then I'll be talking a decent amount about these strands algebras and certain things you can do with them and gluing formulas for them, etc. Okay, so these A of Z is the bordered strands algebra. But first I have to say what Z is. Z is one of these things like this, okay? Z is an arc diagram, which is going to be a compact oriented one manifold, which I draw in black, and then it's going to have a 2-to-1 matching of finitely many points, but not like the boundary points of intervals, okay? Points in the interior of Z, and I'm going to draw those as connected by red arcs. So that's an arc diagram. And I'm not going to put any restriction about that has to have, no circles, or it has to have, any other restrictions on it. It has to be degenerate, non-degenerate, none of that. Just anything like this is what I'll call an arc diagram. Okay, and then how does that represent a sutured surface? Well, given an arc diagram, I'll build a sutured surface, and then if your arc diagram represents your given sutured surface, if the one it builds is the same as the one you have. So how do you build a sutured surface from an arc diagram? You start by thickening it up, take Z times 0, 1. So that would be just this rectangle and then these annuli here. But now I'm going to attach 2-dimensional one handles, just these little strips, okay? According to the matching. And there's going to be a unique orientation preserving way to do this. And actually the orientation on the arc diagram is crucial to make sure that this makes sense, because different orientation can really change the topological type, not just the orientation on this surface. But if everything's oriented, then this makes sense. And now what am I going to do? I'm going to define that's my F, but I define the sutured data on one side of this thickened Z, on say the Z times 0 side. I'll make that the orange, the unstopped boundary. And so that's, this interval in these 3 circles here. And then the rest, including the boundaries of these handles that I added, that's going to become the stopped boundary. And then I get these Lagrangians that basically come exactly from where the red arcs were before, and they're the cores of these one handles that I added. So in this case, this is just the example that we were looking at before. This arc diagram represents this sutured surface, and moreover, gives you a collection of 3 Lagrangians, non-compact Lagrangians, in this sutured surface that stretch from, different parts, these circles in the unstopped boundary, out to this interval in the unstopped boundary. Okay. So that's what I'm saying here. So this is how you get the sutured structure. And now if I want to say I have Lagrangians in the symmetric product, it's just then all k-fold products of like k of these different arcs. That's going to be, so like once k equals 4, there's no 4-fold products of 4 of these 3 different things. So like it's sort of part of this theorem that in this case, for instance, sim 4 and higher is equivalent to that derived category is equivalent to 0. Okay, but this is how arc diagram represents a sutured surface. Now there's a fact about this. I'm not sure if it appears in the literature, but it's a nice exercise. Is that in this generality, okay, your sutured surface can be represented by an arc diagram if and only if the following condition is true. This is more general than what's found in Zarev, for instance. But every component of your sutured surface, not the boundary, okay, your boundary can have components that don't, that are entirely in S plus, entirely in S minus. But each connected component of F itself must at least have some of its boundary stopped and some unstopped, okay? And then you can represent it by a sutured surface. And conversely, anything represented by a sutured surface, by an arc diagram, satisfies this property, okay? And then furthermore, okay, so now let's suppose we have one of these. Then any 2 representatives from it can be related by a sequence of so-called arc slides. And this looks like the following picture. I just take this arc and I take this little endpoint down here and I slide it up around, and now I get this arc diagram, and it represents the same sutured surface, but the Lagrangians have changed. Okay, and so I can think of changing between different Lagrangians, that could arise as part of one of these generating families. I can think of them as coming from arc slides. Okay, so that's one way to show that this is an invariant. The more LOT style way is to show that any arc slide gives you a derived equivalence between these algebras. Or you can relate to Fukaya categories, which don't depend on Z to begin with. Okay, so 2 different ways to see that these derived categories of these partially wrapped Fukaya categories of these things are surface invariants. Okay, so that's the sort of data we pick, and then we define a strands algebra A of Z, which is based on originally defined by Lipschitz, Oshvath, and Thurston. That basically was in the case where Z is a single interval and then has matchings. And Zarev allows Z to have multiple intervals, but still no circles. So for instance, this type of arc diagram is not allowed in any version of Heegaard Floer homology that's really developed, or bordered Heegaard Floer that's developed in generality. But this is the sort of the way the winds seem to be blowing, is that, for instance, Oshvath-Szabo's recent stuff is based on Heegaard diagrams using this. A lot of recent stuff in, say, HFK is trying to allow these closed circles in your arc diagrams. And you can define the algebra even when your arc diagram has closed circles, that the definition isn't so much different, even in the generality of arc diagrams that we gave. It's just the case that sometimes you might have to consider, in generality, curved A infinity deformations of these algebras. Okay, so that's another thing I don't want to talk about, but that's okay. So there's this algebra that was motivated not by Fukaya categories or like symmetric products so much in the beginning, but more by this cylindrical or 4-dimensional or symplectic field theory approach to Heegaard Floer. So that's sort of where people say these come from Rabe chords or something in the contact boundary. That's the original motivation for these, but Arou's work shows that they're closely related to the sort of sim K of a surface approach to Heegaard Floer. So I'll talk about that in just a second.
Can I make you pause for just a second? I got very confused by this statement that you made about, I know you said you didn't want to go into it, but you can allow closed circles and that's related to curvature.
Well, okay, yeah, it's not related to curvature a priori, but what turns out is, so the one piece of evidence I have on this is in LOT's work in progress on bordered HF minus for torus boundary, They're
Mhm.
basically working with a diagram that's like if I have a closed circle, and then I just do the usual so-called torus matching, where it's two red arcs that are sort of linked, not nested with each other, but linked. And now that will give you some algebra. The one I'm thinking of is a perfectly nice DG algebra, infinite dimensional. And what their algebra, and then they look at the sort of k equals 1 summand of that, which would not be DG. But what then they say is, in order to actually count all the disks we want from our Heegaard diagrams and actually get the bordered HF minus theory that we want, this algebra alone is not sufficient. Rather, they consider a curved A infinity deformation, so it has higher actions and it has curvature. And so what I think might be true in general is that there is some more elaborate theory of deformations of these, and that in total generality, if you're trying to do Heegaard Floer, with sutured surfaces as I've defined without any more restrictions and cobordisms between those, then that should probably be like significantly harder than what's currently being done, and more in the character of like this LOT work in progress. So
But
that's why I mentioned that.
so again, this circle would be like a red circle in your pictures on the right-hand side.
Well, orange. Yeah, sorry.
Orange, sorry, it's difficult to.
Yeah, exactly. Yeah, the orange. Yep. The unstopped, the entirely, so that you would have full wrapping, infinite wrapping
Okay.
around that circle. Yeah.
And then
sorry.
all I want to say is that from a symplectic point of view, what I would have expected to say is like, if you try to fill in that circle, then you would see this curvature.
Okay.
But
that makes sense. That's
Okay.
that's consonant with how it works in the things that I know about. I just, yeah, the curvature is in a few different, yeah, I think, yeah, okay, I don't want to commit myself to anything on this, but yeah, what I do know is that the certain like really complicated thing where I also get like higher A infinity terms in the algebra, that does not appear when I'm working with, as far as I'm aware, if I'm working with like this diagram, or if I'm working with the things that one typically uses for HFK, like the Ojala-Szabo things, it seems like these phenomena don't appear. Curvature can still be a useful part of the story, but the higher A infinity actions on the algebra and really having to take a deformation of this algebra doesn't seem to appear in the stories that I'm more familiar with.
Thank you.
Okay, problem. Okay, so now that we have Z, let's talk about A of Z, and we're going to give a basis and then talk about how to multiply and differentiate basis elements. And let me just put up the pictures and then start saying some words about them. This is, for instance, for the Z that we were looking at. This is for a very simple Z that is just an interval with the so-called torus matching, these two nested, or sorry, not nested, but linked red arcs. So what type of pictures are going to give me a basis? What type of pictures am I drawing here? Well, there's something that I draw in just 0, 1 times Z. So if Z was a single interval, then I'll draw a rectangle. Here, if Z is like an interval disjoint union 3 circles, then I'll draw a rectangle disjoint union 3 cylinders, which is really, that's what I'm trying to draw there. It's not entirely clear, but it's a rectangle with 3 cylinders floating on top of it, okay? And then I'm going to just draw on the matching just for convenience. I'll draw which points were matched to which on the left and right of such a picture. So here we have these sort of matchings from the, downstairs up to each of the cylinders. Okay, but then in this template, what I'm going to do is draw some strands picture that I'm drawing in blue. And what this is some sort of strands, some paths up to isotopy, and they start and end at these like points that were involved in the matching. Okay, and they always go consistent with the orientation. So here it's upward veering. I didn't draw the orientation on this arc diagram, but it's supposed to be pointing up, and then the strands have to go that direction. They can't go backwards. Okay. If I have one of these cylinders, I can have strands that go arbitrarily many times around, but it can't like start going in the opposite direction. It can just wrap as many times as it wants in that one direction. So it's got to start and end though at one of these points where the red arcs start and end. Now you can't have any double occupied matchings except, so like since over here, if hopefully you see my cursor here, the little hand, but you see how this blue strand comes into the top of this red arc. Well, that means no other strand can come into the bottom of this red arc. that's not allowed. And same on the starting side. And you might be asking, well, how about this pair of dotted lines? And then I have to say, well, that's the only case it is allowed, is if the strands are horizontal, then the rule is you can't have one or the other. You have to, in some sense, have really what it is it's like a sum of having one but not the other, and then plus the other but not the first. Okay, you can think of it that way, or you can think of it as just dotted lines that you treat with certain diagrammatic rules. Either way, so I'll draw these dotted lines, but they always come in matched pairs. Okay, and then all of these type of pictures I can draw, I form a vector space formally spanned over F2, my favorite field, by these guys. And so, well, okay, I should say what multiplication is. When I say that, the following term, idempotent, will make sense. Right now, I just have these particular elements that don't have any moving strands. They just have dotted strands, just constant ones. So basically, for any red matching arc, right, any of these three arcs, I can choose either I want that pair of dotted lines in there or I don't want it. And these give me sort of special elements of this basis. And these are going to be idempotents for the multiplication. The multiplication is you just line up left to right and concatenate with a few rules to keep in mind. One is that, well, everything is up to isotopy. So once you do this, you isotope except I should say, oh, I didn't even put the relation. That's really bad. It's you concatenate and then isotope, except that if I have a double crossing, so if it crosses once here and then on the other side of the multiplication, it crosses again, so that the isotopy would sort of remove two crossings, then I declare the product to be 0. Okay, so I only allow multiplication in cases where that doesn't happen. Okay, and then it's the following rules. Then the strands have to line up. So I can't like come in and then leave the matched one or anything like that. You know, the strands have to be concatenable. Now what happens if I try to concatenate a moving strand on one side? Okay, a pair of dotted with the same pair of dotted on the other side, that just gives you the same pair of dotted in the product. But what about moving times a pair of dotted? Well, here's where this, it's really the sum of one but not the other sort of thing comes in, is if I have a moving strand like this, coming in and I multiply, what this is going to do is just pick out this bottom one to solidify, erase the top dotted one, and the resulting thing will have a strand that looks like this. So that's the rule for the dotted things. And then in the differential, and so this specified this together with the important rule that I forgot, that the double crossing gives you 0. This gives you multiplication on these basis elements. You can check it's an algebra, and then it's also a DG, or at least a differential algebra. It has this differential where if I have a crossing like this, then there's a term in the differential that resolves this crossing. It's over F2, so just have coefficient 1 out front. And then you sum over all ways of resolving one crossing like this. That's the differential. Now what happens when I have like a moving strand that goes through one or both parts of a dotted strand? Well, again, it's sort of pick one and erase the other. That's the philosophy, and it's the sum over all ways of doing it. So I see this crossing point here. This is going to give me a term of the differential where I solidify the top one, erase the bottom, and then resolve, and I get this. But I could also solidify the bottom, erase the top, and then resolve, and I would get this other one. So you'd have these two terms in the differential of this picture. Okay, so this gives you a differential algebra. Now, you might think there's like a grading by the number of crossings or something like this, but in fact, these dotted lines mess it up, because you could have like, here's my moving strand, dotted here crosses it, but then it's matched to another one that doesn't cross it. So it's actually, this is a sign of these are really tricky to deal with in a grading point of view. LOT show that if you want to define a Z homological grading such that these basis elements we just gave are homogeneous, that's impossible. Even in the simple case of the so-called torus algebra, and in most cases. But there are cases where it is possible, on the other hand. And so like our example that we were looking at, you know, 3 circles each matched to a line, the gradings work a lot better there. But in already very simple cases that are not that, though, you can't define any gradings. So, or you can define gradings, but like they're these non-abelian group value gradings, and they're technical to work with, and I'm not going to discuss them here. So this though is what I wanted to say about these algebras. These are certain combinatorially defined things, and then what Aru shows is that these actually describe endomorphism algebras of the corresponding product of red arc Lagrangians you would get in the sutured surface associated to F. Okay, so I pick this Z represents F. This gives me these Lagrangians, so I can take their endomorphism algebra, but the Z also gives me this A of Z. And non-trivial fact is that these are isomorphic. And how do you show this? You consider a particular diagram. So if I want to compute the endomorphism algebra of these red arc Lagrangians a priori, I'm going to draw some sort of picture. And I hesitate to say that I'm not sure the right version of this picture is correct, and that I'm not sure I'm supposed to do. I just wanted to make it look symmetric. But like the idea is that I take 2 copies of these Lagrangians, right? If I want to compute endomorphism algebra in a partially wrapped Fukaya category, I would take 1 copy and wrap it, and that's what I see on this left picture. And then I wanted to draw it more symmetrically. So if you prefer, maybe these red ones just go right in and don't wrap at all. I don't know. Okay, but I'll draw pictures like this regardless of, maybe I'm revealing that I don't know so much about, as much as I should about these things, but that's all right. So you have this type of diagram, and so sort of a priori, if I take a Heegaard Floer like chain complex associated to such a thing, then that should give me as a chain complex some sort of endomorphism algebra between these Lagrangians in the Fukaya category. And then you can try to talk about, well, the differential should be the sort of Heegaard Floer style for doing Lagrangian Floer homology in a symmetric product type of differential that you have here. And then you should also be able to describe the multiplication in sort of holomorphic terms. And so that's how you would define the endomorphism algebra. And on the other hand, we have this combinatorial strands algebra. Okay, but there's a combinatorial observation you can make, which is sort of the core combinatorial idea behind this Aru result, as far as I understand it, is that if I look at the so-called Heegaard Floer generators, oh crap, okay, my picture is cut off a little bit. I don't know how that happened. It's not cut off on my, okay, that's better. I think that's not cut off now. Okay, so if I have a Heegaard Floer generator on the left, it turns out that that corresponds uniquely with one of those strands pictures. It's not entirely obvious what the correspondence is, but here you can see, for instance, my strands generators that would have wrapping a bunch of times are on one of these cylinders. That means you have this red arc intersects deeper and deeper and deeper with the wrapped blue arc, okay? And then the example I wanted to draw was this particular, so I guess you'll have to take on faith that there is some natural combinatorial correspondence here. This is sort of contained in Aru's theorem, that this sort of Heegaard Floer generator, this would be a generator a priori of the endomorphism algebra. This actually lines up with, you can draw this picture on the other hand, and down here, you can draw this strands picture, and the differential from resolving crossings corresponds to sort of counting this rectangle here. And that's the one I knew these generators, because this is the one like simple differential that I see on the Heegaard Floer side here. And on the other hand, on the strand side, there's only one, crossing resolution differential like this that I'm going to have. And so it's easy to see that these are the right ones. Okay, in general, there's some very natural identification of these things, and then doing work, you can show that the differential and the multiplication on the strand side agree with the ones you would get on this holomorphic side, so that this strands algebra really does describe the endomorphism algebra. And then you have to show generation, which is, as far as I understood, like Aru was a little bit cautious about that in 2010, but as far as I understand, those issues are resolved now, possibly by people here. So that's, I again, something I don't want to try to commit myself to now that the audience is getting larger as well, but that's okay. Okay, so this is what I wanted to say. This is sort of the background of the cast of characters, and then I want to talk about how would I glue these things together from smaller pieces. Okay, say I had this picture. Let's look at the 4 circles in the middle version instead of the 3, and say I wanted to cut that along this purple line here. Or equivalently, say I had these 2 pictures and I wanted to glue them along these little purple segments of their boundary to get this left picture. So how does the strands algebra or the Fukaya category of symmetric product of this side relate to those of the 2 pieces here? And this is sort of the first question that's considered in Douglas Manolescu's cornered Heegaard Floer homology, and then further studied by Douglas Lipschitz Manolescu. But let me just say at the level of arc diagrams, this is what it would look like. You know, I can just see if I just take the orange and red parts here, this is what it looks like. And it looks like, on the other hand, gluing 2 arc diagrams along a single point. Is that saying something about a Heegaard Floer of a point? I hope so, but again, let's move on. But so you can ask similar question in terms of these Aru-Zarev diagrams. If I'm saying instead of strands pictures, I'm going to look at a Heegaard Floer complex of this. Well, how is a Heegaard Floer complex of this arising from, well, it doesn't look like it can quite arise just from the Heegaard Floer complexes of these things, right? Because there's like all of these intersection points here that here we just have sort of one intersection point in the middle and then all of the wrapping ones. Here, same. And then now we have 7, well, I can't count. There's a bunch of intersection points in the middle here. There's like 10 of them. Well, okay, it depends on if you count these guys as part of the wrapping. But anyway, like it's not entirely clear just looking at this, how you're going to get the Floer complex of this thing if you only know the Floer complexes of this. And in fact, Douglas Manolescu are going to try to recover this from these guys plus extra data. Okay, and then we'll talk about how to think about that extra data. But this is the question of cornered, and then this is cornered Floer homology for the 2-dimensional invariants, for the surfaces. And then you can also talk about for 3 manifolds with corners as well. But I'm just going to be talking about the 2 and 1-dimensional parts of it today. Okay, but so one thing you can say is if here's my like typical strands picture I would have in the algebra of the glued together thing, what it looks like is it looks like it has a top piece and a bottom piece. And, you know, if I draw it like this, it looks like I could take the top piece to be something like this, where the strands sort of emerge from the bottom and go over to the right-hand side. And the bottom piece would be strands, you know, go up to the top so that above they can emerge from the bottom. So that's sort of what it looks like you should do to piece together this algebra, and that's what they do. So you can view this as follows. These type of pictures where you have sort of K strands emerging from the bottom, these form a bimodule over the strands algebra. Because after all, your strands algebra is those things that have 0 things emerging from the bottom. I can multiply on the left or right using the same rules as before. You know, if K things emerge, I multiply on the left or right by an algebra element, I'll get another thing where K things emerge from the bottom. So that's an action of this algebra on a bimodule. Same for the bottom ones. Okay, so what it looks like is you want some type of formula like the algebra of the glued together thing is a direct sum over all possible numbers of strands that go through of the top thing tensored with the bottom thing, but you got to be careful that crossings are allowed to float through. So if we look at this picture, we see this crossing up here on the top, but on the left, I can equally well isotope that so they cross on the bottom piece rather than the top piece, and I got to allow that. So that means when I take this tensor product, I'm going to do it over a certain algebra that has various names. In our paper, we refer to this as a certain differential instance of a nil-Hecke algebra. In Douglas Manolescu's paper, they refer to this as a nil-Coxeter algebra. And regardless, it pictorially is generated by these type of pictures. So there's like K-1 possible pictures. There's not over or under crossings. It's just a singular crossing, multiplication on this, and then, you know, I get more things by multiplying these basic generators by stacking them on top of each other. And so these are multiplicative generators. unlike the basis elements we had before, these are multiplicative generators, and the relations are, if I have a double crossing, that's 0. That's very similar to the rule I forgot on the slides for the strands algebras. You also have this R3 move rule. And then the differential is given by basically resolving crossings. Some overall ways of resolving crossings. So on the generators, that just says D of any one of these generators is the identity. Okay, so that is some algebra that if I tensor over it here, then that will allow crossings to pass from top to bottom. And so Douglas-Manilescu's theorem can be stated as follows. Algebra, if Z is Z1 union along a point with Z2, then the algebra of Z can be described as follows. And so I want to think of this like this in terms of the Aruzarov diagrams. Here's my thing on the left. And if I really want to look at what I have in terms of cutting along the middle and having two pieces, I can think of it as follows. I have this old diagram that I had, but I have these two. Notice how there's like 4 red arcs starting at the top on this one. So there had better be 4 red arcs starting, on this one. But 2 of those are going to like go downstairs. They're going to go to the other piece. So right now they don't do anything. They just sort of pass through. And on the other hand, if I'm looking at the bottom piece, I can tell the same story, except that it's a couple blue arcs. These ones right here that look like in this picture, they're just up and passing through. And then these pictures, all I got to do is notice that there's this little bit that's just, and it's going to be K parallel red arcs in general, hatched with K parallel blue arcs. And there's going to be, whenever I'm doing a little end-to-end gluing of these arc diagrams could have all sorts of stuff elsewhere, but when I'm doing one of these gluings, what I'm going to see is just identify some piece like this with some piece like this. Okay, and now I can draw this in I sort of, how does this diagram relate to the one we looked at before? Well, here's the one we looked at before with just 2 little red arcs added. And if I think of sliding these red arcs and going up there, which isn't going to affect so much the complex, then this is basically the same picture. And similarly down here, this is like the diagram that I had before, but with 2 blue arcs. So what we're thinking is that these MK and NK bimodules, one way to think about them, other than strands going up or strands coming down or any of that, you can also think in terms of these Aruzarov diagrams, and then you add these, if it's MK, I'm going to add K of these extra parallel red arcs there. And if it's NK, I'll do blue ones. Okay, and so this gives a nice way. So identifying these green boxes is very much like tensoring over this Milch-Oxeter algebra. In fact, already in this Douglas-Manilescu paper, they show that this NCK is the Heegaard Floer complex of like this hatched picture, which is basically can be understood, and it's a grid diagram more or less. And so that's something that's already in their paper, is that once I see like identifying this hatch picture with that hatch picture, that looks exactly like tensor over NCK. So you can kind of see this Douglas-Manilescu formula in the Aruzarov diagrams, which I think is nice. Let's see, wait, is there a...
I can ask my question out loud. So
sorry.
I would have naively expected that what you would see is like I intersection point at the top and J intersection point at the bottom, and I plus J equals K.
Yes, that's right.
But that's not what you seem to be
I
writing.
am considering all possible numbers of intersection points together. So my K is like number of strands that go through, not, so like,
okay, I think I see. K is the number of strands. I see. K is like the label for the bimodule, not for the algebra.
Yeah, that's right.
Okay, great.
Algebra also has this label that's additive. There's this number of occupied arcs or whatever, and that is indeed additive the way you're talking.
Okay, then can I ask, I mean, I know we're kind of, you have much more to cover, but this thing that's happening in the green box looks to me like you would just look at the category of the symmetric product of just, a disk with 2 black arcs.
Yes, exactly.
On 2 sides. Is that described anywhere in the literature? Or rather, is this action described anywhere kind of flirt? I mean, I understand this is a description in terms of arc algebras.
I know. I mean,
so it's like my job or Denis' job or somebody like that to do like a Fukaya version of this.
Well, I don't know. I mean, it's something, I guess, yeah, it should be this U thing that we're talking about. I mean, I think it's, in some sense, some version of that statement is already contained in Douglas Mendelewski's statement that this NCK algebra is the Floer complex of these things. And then, if I take these things, but I allow, like, if I take inside this disk, I consider the following redundant generating set of Lagrangians. I consider all possible like products of k parallel copies of this one thing. Whereas to generate, I wouldn't need k greater than or equal to 2 is redundant here, but still I can define this thing and look at the endomorphism algebras of each of these. And this is, so when I talk about this monoidal category U in just a second, that is, and I think that's, I mean, is there something to, I think in general, it would be good to give a more like, why does one have an action of this on partially wrapped Fukaya categories without looking at, oh, I have strands going up and whatever, but say a priori from a geometrically motivated point of view, why this thing acts, etc., and why there's a tensor product formula like this. I think that would be excellent. Raphael and I both, I think that would be really excellent.
Thank you.
There have been people pushing us to, say how it works in that sense. I don't know if it would definitely be good to talk about.
No, I think this talk is great. This is exactly what I want.
Awesome.
Thanks.
Great. Excellent. So now, and it seems like I am getting behind, but I think I'm actually not so far behind because this is, so if we understand this to this point, that's very good. I just want to note that there's a couple limitations of this formula. And one is that, okay, well, we started by saying we want the complex of this from the complex of these, but, without these extra red arcs. So really what we're doing is, recovering algebra of this glued diagram from the algebras of the two things plus some extra data. Okay, so it doesn't quite look like it's answering the question as stated. It looks like you need this extra data on the other hand. And what this ends up telling you or causing another limitation is that what if I then want to glue like an extra diagram on the top, another Z3 on top of Z1 union Z2. Geometrically, that seems very natural, but what you would need for that is then bimodules MK or NK for the glued thing. And that is found nowhere in Douglas Mendelewski's paper for a sort of conceptual reason, is that they don't think of it in terms of these Zarev arc diagrams. They're thinking pointed match circles, that they're cutting a circle sort of in the middle. And then only when you have this sort of weird half of a circle with a half of a base point sticking off, are you going to have these MK and NK bimodules? And that's the perspective they take following LOT, which Zarev was basically, his thesis came out in the same year as Douglas Mendelewski, so you can hardly blame them. But from this point of view, it's not clear that, that you should be able to do this multiple gluing with anything like these same techniques. That the multiple cuts would look like, now I have this circle and I'm cutting it twice, and now I have this weird double interval thing in the middle, not a half circle anymore. But if you take the Zarev arc diagram point of view, it geometrically looks very natural to try to do this iterated gluing. Okay, and in particular, I have strands going up module, so I might ask, like, can I recover not just the algebra of the glued thing, but the MK or NK bimodules of the glued thing, given the same data for the two pieces? And that ends up being true. And I want to suggest a way of thinking about it and thinking about this. And that is going back to what I said near the beginning. I don't want to just think of, if I have a sutured surface like this, I don't just want to think of the Heegaard Floer invariant of this as being encoded by the algebra, being this Fukaya category that's really a sum of different pieces that don't interact. I really want to think of the true Heegaard Floer invariant of the sutured surface as being that, together with some extra data that's going to be encoded by these bimodules MK and NK, and that's going to relate sort of the summands of the algebra for, so how this K, by the way, interacts with the sort of I and J in the comment is like your MK bimodule is going to like decrease that I number by K. So it's going to be I minus K on one side, and on the bottom, it's going to be like J plus K. Okay, so so that's what's going on. And so you might, so the Heegaard Floer invariant should be like something encoded by this algebra and all this bimodule data, but how much do you need to remember about this bimodule data? Not that much. the K-strands version is just a tensor product over the algebra, or iterated tensor product of the one-strand version. That's a theorem that you can prove about the combinatorics of these strands pictures, is that you can factor it as a tensor product like this. So if I want to remember all these MK and NK bimodules, I just need to remember M1 and N1. And in fact, they're adjoint to each other on one side. And concretely, like, well, projective on one side, and you just sort of take the linear dual and get, or the algebraic dual, I mean, and get the adjoint on the other. So they're related in this very transparent way algebraically. So you just really need to remember one of them. So let's remember N1. That's a convention of our paper. Let's call it E. So the Heegaard Floer invariant of the sutured surface shouldn't just be encoded by A of Z, but it should be encoded by A of Z, and then some bimodule E, and then something that recovers the NC of K action on these things. Well, the minimal thing you need to recover that is just a single endomorphism for a single crossing, and that's going to be an endomorphism of, well, N2, which is going to be E tensor E, and it's got to satisfy the same relations that we said before. So the upshot, what I'm trying to argue for is that the Heegaard Floer invariant of a sutured surface, and oh my gosh, I was going to put in that same figure again, but I just said figure in the slide, okay, go figure. But this is, it should be encoded by this sort of triple of data, the algebra, the bimodule, and then this tau endomorphism. And what this is a two action of a particular monoidal category. Maybe I'll go a little bit fast here. I don't want to, get too into the algebra, but I can define this monoidal category where the objects are just your natural numbers, and then an object, when I have a two action of this on some DG algebra, then an object of the monoidal category is going to get sent to a bimodule over the DG algebra, and then like your monoidal structure on objects will get sent to tensor product of bimodules. So here, if on my natural number is n greater than or equal to 0, well, 0 is going to act as the identity bimodule. 1 is going to act as my bimodule E, and then n is going to act as E tensor n, if I have a two action of this thing on my A of Z. And then, okay, so but that's what the objects in this U plus are. The morphisms in this U plus are just all of these Nilcoxeter algebras. But then morphisms from two objects that are not equal to each other, then those are just 0. So all of the morphism spaces in this thing are just built from these endomorphisms of n for every n, these Nilcoxeter DG algebras. And so if I have a two action of this on some DG algebra, what that means is that all of these Nilcoxeter elements are going to act as endomorphisms of the bimodules. Like if I have something in NC of n, like I'm saying here, that will act as a bimodule map on E tensor n. So having this data is what we have. We have these bimodules for every K. We have these Nilcoxeter actions. What this means algebraically, or one way to just package this, is say we have a two action. So this is like a monoidal functor from this monoidal category U into the monoidal category of bimodules and bimodule maps over my algebra, maybe DG bimodules, okay, with the monoidal operation being tensor product. Okay, and I can equivalently view this as an action on the derived category by functors and natural transformations, rather than by bimodules and bimodule maps on the algebra. And then I can then think of it as an action on the Fukaya category, and then one would like to have a correspondingly geometric construction of this rather than just translating the algebra. So that's as we just talked about. But what is this U plus thing? Well, it was introduced by Kovanov in 2010 and categorifies the positive half of UQ of GL11. So I just want to paint a suggestive picture maybe, is that if I'm looking at the type of sutured surface like this, I can think maybe these internal circles, I label them with the vector representation, and then on the outside, I get the tensor product of these representations. At least maybe you've seen situations where something like that is true. Something like that is also true here. And you can say things about this and, the Heegaard Floer algebra of that particular example versus GL11 representations. But what we're seeing here is that we have this sutured structure in the boundary. So the boundary is not just a plane circle, it's sort of two intervals glued together. And on the other hand, what sort of action do we have? It's of the positive half of GL1, it's of this categorific this categorified positive half, this U plus thing. So somehow that seems like related to circle versus interval. But in general, you know, the sort of thing that we get in this, by doing this construction in general, is that if I have a arc diagram Z, then for every interval component of Z, okay, not circle components, we don't know about actions from those yet, but for every interval component, I get some 2 action of this U plus guy on my A of Z, such that all of the 2 actions for different interval components of my arc diagram are all commute with each other in the appropriate higher sense with commutation data, stuff like that. So that's sort of an algebraic description of sort of when I have this sutured surface. So equivalently, if I say this sutured surface with certain unstopped intervals in its boundary, then I'm going to say the Heegaard Floer invariant of that is going to be like this derived partially out Fukaya category, but then equipped with the 2 action of the Fukaya category of the disk, maybe one of those actions for every unstopped interval in the boundary of my original surface, something like that. So that's the picture. And then so given this picture, this is the last thing I want to say, how do we think about this tensor product, or this gluing, the Douglas-Malinowski gluing operation, which in the example that we gave looks like something like a tensor product. If I believe that like a genus 0 surface with all of its punctures labeled by, you know, some representations, then that surface should get the tensor product of those things. Then it looks like this gluing operation is related to tensor products, and in fact, it is. So if I have these 2 actions of U plus on some stuff, I can ask, okay, if I had the quantum group downstairs, I could take a tensor product of representations. And so this is something people would really like to do in the categorified setting. Raphael has been working on this for a long time and has a very substantial body of work on this that unfortunately has not hit the literature yet, but hopefully soon. So even in like the SL2 case, that's not known. But in the GL11 case, a sort of miraculous simplification occurs, and it's actually related in a highly non-trivial way. This whole theory that Rouquier has been working on is related to what Douglas-Malinowski were looking at from a completely different point of view. So what we show is that there is this tensor product operation in the case of U plus, whereas Rouquier's work will cover categorifications of Cox-Moody Lie algebras, which this is not, but this is a sort of simpler and yet different thing. It's a sort of categorification of a super algebra, positive half. But there exists, so if I have 2 things that have 2 actions of this thing, then there's a sort of tensor product way of combining it. Get another thing that also has a 2 action of U plus. And there exists such an operation compatible in the appropriate sense with the one Raphael defines for Cox-Moody examples, such that the Douglas-Malinowski formula becomes that the algebra of the glued together arc diagram is the tensor product. And then, so once we have this, then there's a natural further thing you can prove, that this is not just true as DJ algebras, but this is true also with respect to the higher structure that you have on both sides. So that now I can apply this iteratively. So it sort of tells you how to build the extra MK and NK bimodules for the glued together thing. And this, the last thing I want to say is a little bit about the, okay. Yeah, the last thing I really want to say is, okay, so how would you define this tensor product? Well, one way to think about it is you use a formula like Douglas-Malinowski to get started. You can translate this more into the language that Raphael uses, which is more categories and functors rather than algebras. But this ends up being very, very closely related. You define A with this Douglas-Malinowski-like formula, and then to get the higher structure, they're similar types of formulas that are just a little bit more involved. And you have to prove certain algebraic consistency. You have to prove that this whole thing, AE tau that you get gives you, and then the tau, okay, tau would be like some complicated matrix on these things. There's a way to describe it using string calculus. And then these proofs that this AE tau thing is well defined. It's basically a sort of standard-esque type of argument in 2-category theory, where you draw these string diagrams and you have these relations and you check that they're all true. Or you can do it all with symbols as well. And we wrote up both versions, preference in our paper. So everyone you prefer to read. But visually what's going on with this this E bimodule is that you sort of have two types of, so if I look at strands, one strand going up, then there's two ways that can happen in the glued picture. The strand can come from the bottom bit or the top bit. That gives me my two summands here. There's a differential mapping between them. That's going to say, I'm going to, resolve this crossing in a way that changes the generator of the first type into generator of the second type. Okay, so this is, and I think I am out of time, so I have maybe one.
I think you can take a few minutes to finish. It's
okay, so I just wanted to say, because I wanted to think, because I was encouraged to think about and maybe say something about the case of Sim 1, which I think is interesting because there's a lot known about Fukaya categories of Sim 1 of a surface, i.e. the surface itself with some stops on the boundary. So I just wanted to just write what I could say in this without really saying anything interesting maybe, but if I expand out the above formula for A, this is like the Douglas-Mendelescu formula, and just write out the sum in K. So the K equals 0. I'm just taking tensor products of 0 copies of these bimodules, so I just get the algebra itself. And then in the next summand, I have tensor product of 1 copy. And then in this summand, I'd be tensoring over NC2, etc. But if I only care about like the Sim 1 part, what I'm going, and now we see these numbers, these sort of other numbers that are not the Ks that were coming along. So if all I care about is like Sim 1 of the surface, then these are the only 3 summands in the formula that are relevant for me. I have like strands, it's like picture with only a single strand moving, okay, and no other strand, like only a single strand occupied at all, only a single strand exists. Maybe it's like a dotted pair, but only one dotted pair or one moving thing, okay? So either that's contained on the top, that's this top summand, or that's contained on the bottom, that's this other summand, or it goes through, and that's this bit where it's, if I take this bimodule, where one strand comes up from the bottom and there's no other strands at all, and then I take this bimodule on the other side where one strand goes up to the top and there's no other strands at all, then I just take the tensor product of those over the ground field, because there's not like ways for a crossing to pass if there's only one strand, okay? So so this is what I would get if I want like the Fukaya category of the glued together surface. And I noticed like, okay, this would be like the endomorphism algebra of some generating Lagrangians and that thing. And so like in this algebra, the idempotents, the basic idempotents I'm gonna have are only coming from the first 2 summands, where it's just like, if you basic idempotent of the first one or basic idempotent of the second one. It's just you take the disjoint union of these set. It's like saying you have your Lagrangians on one side, these are your generating ones. Lagrangians on the other side, those are your generating ones. And then my generating set for the glued surface is just the union of those. So no new things that like cross or anything, just your Lagrangians on one side or the other. But now there can be morphisms from a Lagrangian on one side to a Lagrangian on the other side. And that's where this third piece comes in. So, right, so morphism complex on one side, in one direction, the morphism complex will be 0. In the other direction, it will be given by this type of summand. And then I wanted to just maybe raise a question, is that what are these things? I mean, if I want to think of these, I can think of them as bimodules, but action of the zero strand algebra is just the ground field. So I can really just think of these as DG modules over the strands algebra. And then I can ask, well, shouldn't they have some interpretation like immersed curves or something like this? I don't really know. I think like what the answer, I think like definitely the theory says there should be an answer, right? But I don't entirely know. The one speculation, one thing is that these are not projective bimodules. So it's not like they come a priori as a complex, like a twisted complex or something like this, but you can take resolutions. But I just wanted to speculate that if you have such an interpretation, mayhaps it's related to these little things, these little extra lines I drew in the Aruzarov diagrams before, which I'm trying to find the right picture for it. Yes, here. So like if I want to make a guess as to what these bimodules look like in terms of immersed curves, the best guess I can give right now is something having to do with like this little extra line I would put if I had k equals 1, or this little extra line. Okay, but that's all I had. I'm sorry for going over. But thank you very much for coming and for inviting me again. And I'd be happy to try to answer any questions that you might
Thank you very much. Let's thank Andy again, especially for all the effort that he put in communicating with us and trying to explain so many things that I'm sure are very basic. Are there any questions?
Hi, I had a question.
have.
Go ahead.
So I guess you didn't really cover this, but I want to ask about, like talking about invariance of like cornered three manifolds,
Mhm.
right? So in Douglas, Lipschitz, and Manilescu's original paper, right, there's this funny thing where if you want to define the cornered invariant of like a cornered Heegaard diagram, you have to like, if there's higher A infinity actions, you have to like take a projective resolution before you can like attach like the cornering bimodule to like get the cornered invariance, right? And so it's kind of like you're DGifying everything before gluing. And I was wondering if you know how to like rectify that, and if there is a way to like have like define like a partial box tensor product or like A infinity, like partial A infinity tensor product, like yeah.
What I would say is this whole Zarev point of view encourages you to think slightly differently than the pictures that are in those papers. So what I want to be getting at next, and in terms of the three-dimensional content, and like the sort of pictures in my paper from December, are these sorts, where I have, rather than thinking I have a closed three manifold, I'm cutting along a closed surface, and then I have another closed surface cut, and then I have these four pieces, okay? Instead of that, I want to think more relative, like I have one of these Zarev pictures, like a single interval, maybe with the torus matching. And then maybe I have some very simple Heegaard diagram that I draw on a rectangle, okay? This would be like a bordered sutured Heegaard diagram. And so, yeah, so then one should get, as long as the diagram satisfies certain properties, one should get a morphism of two representations. So the bimodule should be able to be upgraded, just like the algebras were upgraded. And then there should be a sort of formula for taking tensor products of one morphisms, an algebraic formula. And so this is all sort of the way I have been preferring to think about it, and that I'm going to be aiming towards hopefully in future work on it. And I'm not like translating exactly with what Douglas Manilescu and Douglas Lipschitz Manilescu do on this stuff is not something I've tried to do necessarily yet, just because the difference in these perspectives, like they're not going for bimodules, for instance. So I mean, I know they're looking at cornered curve counts, and I also see those in like what I want to do, but beyond that, can I compare more precisely? I'm not sure yet. Hopefully I'll be able to, understand a bit better how their stuff works eventually. But right now, yeah, I've been thinking from a slightly different angle.
Okay, thanks.
Any other questions? Okay, I actually have a long list of questions, but maybe I'm going to pick one of them for the
Okay.
record, and
Okay.
then
Yeah,
we can
answer.
maybe discuss later. So what happens for, I mean, is there a similar picture for Khovanov homology?
Only in this unpublished work of Raphael, where there's this tensor product operation, and then one could hope that there is, you can do it geometrically. I think Nina Aganagic is working on versions of Khovanov homology. They're very similar in spirit to Heegaard Floer, but they're going to use certain figure 8 curves where Heegaard Floer would have the straightened version. But if so, I mean, one could, if one tries to cut those diagrams up locally, I presumably can treat them using similar ideas. But the question is like, yeah, will Raphael's SL2 tensor product, which in the end is a bit more sophisticated in terms of its A infinity complexity than the one here. Everything here was just DG. But in SL2, case of Raphael's stuff, you have to do infinity apparently, which I'm not so familiar with that construction myself, but I'm curious how much that has to do, because I do think, yeah, there's indications that you can treat SL2 in other cases with similar techniques.
I see. So basically you're saying the issue is the issue of this tensor product.
That's one issue that I know of, is that like, I mean, I could imagine this U plus tensor product being relevant. Now, what would especially be interesting is a real good geometric side to this Raphael SL2 tensor product.
Yes.
I think that would be the most interesting. The other stuff I would want to understand exactly, like if it's really, you know, sort of using the connection to GL11 to understand SL2, that's great. But even better is like understanding both GL11 and SL2, you know?
Yes. So I just want to make a comment, which is that, you know, I mean, regardless of whether Mina's ideas for doing a Heegaard Floer-like construction, basically symmetric product construction of Chovanov works out or not, there is so I think of that as like a 2K dimensional manifold. There is
there's the 4K version.
Right. So there's a 4K dimensional thing. I mean, Seidel-Smith already have a theory that gives us Chovanov. So I guess I haven't thought about whether to build things there. So my first question was to ask whether algebraically they exist. So basically you're telling me algebraically, maybe they will exist once Raphael is done with his.
I think so. And I would expect that his work has lots of relationships with that type of geometry. I don't know. So I can't really, comment with authority on that, but I can speculate. And I think that's
okay. Any other questions? Okay, I guess there's no more questions other than my long list of questions. So I suggest we thank Andy again, and then we'll stop the recording.